Today's topic is projectile motion. I will talk about what is projectile motion. I will briefly discuss the necessary background knowledge to derive mathematical expressions. I will derive mathematical equations of projectile motion. I will present this derivation in a more convenient method. Specifically, I will derive equations for the height and range of the projectile along with the time of its flight. In the end, I will solve an example of projectile motion. You will understand what constitutes a projectile motion and solve the projectile motion problems as well. Let's observe something before we can talk about projectile motion. I have a horizontal line here. I have labeled it as x, or I can call it I unit vector. Similarly, I have a vertical line here and I can call it y, or I can call it as j unit vector. These lines will serve as reference. Suppose I have a block at the origin. If I apply a vertical force on the block will move vertically in the direction of the force. If I apply a horizontal force on the block will move horizontally in the direction of the force. Now if I apply a force diagonally, the block will of course move diagonally in the direction of the force. We should understand an important point here. The force is slanted. It means it's neither horizontal nor vertical. As a result, the block moves horizontally as well as vertically at the same time. We can also observe some other things. For instance, if the force makes an angle of 45 degrees with the horizontal line, the block covers equal distances horizontally and vertically. If the force makes an angle that is less than 45 degrees, the block moves faster horizontally and slower vertically. If angle of the force is greater than 45 degrees, the block will travel more vertically and less horizontally. Do you know the reason behind slowing down in one direction and getting faster in other direction? I will explain it in a moment. When we apply a force on a body, it moves under the effect of that force, and this movement is acceleration. This is famous second law of Newton. Force equals mass times acceleration, where F is for force, M is for mass, and A is for acceleration. Force and acceleration are in direct proportion. It means more force, more acceleration. Similarly, less force means less acceleration. Suppose we have a vector f somewhere between x and y axis. The vector f is making angle theta with the x-axis. I want to know about the horizontal and vertical components of vector f. For that, I can draw a perpendicular from the tip of vector f to the x-axis. Similarly, I can draw another line from origin to the point of intersection of the perpendicular. Now I can label origin as O. Let's call this point as A, and this point can be called as B. I can further label the lines. For example, the line AB can be labeled as F subscript V, because this line is representing the vertical component of force F. Similarly, the line OB can be labeled as F of H, because this is the horizontal component of force F. Before we find horizontal and vertical components of vector force F, I want you to notice something. The triangle OAB is actually a right angled triangle, and this angle is actually 90 degrees. Next, trigonometry tells us about a ratio which is sine of theta, which is equal to perpendicular divided by hypotenuse. If I use the triangle OAB, the sine of theta should be equal to, the perpendicular is my vector f of v divided by hypotenuse is this line of the triangle, which is vector f. Because I am interested in finding the vertical component of the force F, so I will isolate f of v from this equation. So if I multiply this equation with vector f, I will find f sine of theta equals f of v, which is vertical component of force F. So observe one point here, that vertical component of force F depends on the theta. Theta is the angle which the vector force F is making with the horizontal line or x-axis. Another ratio which is cosine of theta for a right angle triangle, the cosine of theta is equal to base divided by hypotenuse. Remember, base is the horizontal part of the right angle triangle in our case. Now if I plug in the values of base and hypotenuse into this equation, I will find that cosine of theta is equal to the base, which is the horizontal part of our right angle triangle, and I labeled it as f of h because it is the horizontal component of f. Hypotenuse is same f. Once again, I will isolate f subscript h because I am interested in finding the horizontal component of force F. I will multiply this equation with F to find that the horizontal component of force F is equal to F cosine of theta. So here I have vertical component and here I have horizontal component of force F. So these trigonometric ratios sine of theta and cosine of theta help me to find vertical and horizontal components of force F. Let's rewrite vector F. F is equal to f of h, and I can write it as I unit vector, plus f of v along the j unit vector. So this equation tells us that vector f is split into two components or parts. One is horizontal component, another is vertical component, and I and j are telling us along which direction. For example, I is for horizontal component, j is for vertical component. Now because I know the values of horizontal and vertical components of force F, so I will just plug in these values into this equation. So F is equal to F cosine of theta along the unit vector I plus f sine of theta along unit vector j, which is actually the vertical line. We conclude from this equation that the horizontal component depends on the ratio cosine of theta. Similarly, vertical component depends on sine of theta. Next, we should study the behavior of sine of theta and cosine of theta.